Hello everyone, welcome back. In my previous video, we talked about one of the most misunderstood numbers in Linux, CPU and memory usage in the top command. Today, I want to talk about another command that almost every Linux engineer uses, but very few people truly understand, which is, as you can see from my screen, the free command. As I said in the last video, I worked as a deployment and integration expert, and throughout my career, I've participated in countless troubleshooting sessions, production incident, performance investigations, and customer escalations. And one of the things that I've noticed is that whenever memory becomes part of the discussion, someone's inevitably run 3-H or 3-G, whatever he used to. Then all eyes immediately go to one column, which is, as you can see from here, the free part. Okay, and maybe they see, as you can see here, they see a few hundred megabyte left. Then someone says we run out of memory in this case. Another person notice swap is being used, maybe. Then somebody else says the server is swapping, we need more RAM. And suddenly everyone is convinced that they found the problem. The funny thing is that many times there isn't a memory problem at all. I've seen engineers add the memory to perfectly healthy servers. I've seen application restarted because people thought Linux was out of RAM. I've seen incident escalated to vendors simply because the out of memory issue and simply because of this column, the free, which we are talking about, and was misunderstood. The reason is simple. The column most people watch is not the column that tells you whether your system is out of memory or not. In fact, one of the numbers shown by free is very misleading. That if you use it to judge memory pressure, you'll often reach the wrong conclusion. So, in this video, we are going to fix that. We'll break down every column in free-h. We'll trace each value back to the Linux kernel, and we'll take a look basically inside the proc meminfo. Okay, so let's get started. As you can see here, let me take a screenshot as usual here. Okay. Um, as you can see, we have here, this is actually the Postgres database, and I chose it for a reason. I'll show you why. Um, Here you can see the server has a 23 gig, and there is only 3 gig used, but we have in the free part we have only few megabyte, which is like a half a gig less. Okay, and we have shared. We'll talk about this. Also, the shared is 8 gig, and the buffer cache is 19 gigabyte. But at the same time, you can see here also we have 11 gig available. So there is a lot of people, and I've seen senior engineers raise this. They have more than 10 years of experience, as I said in the first video, and I know this is might seems weird, but trust me, if you go through so many projects, you'll find those people. So uh, 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 they look at the free command, the free and the free command, and they say, "Oh, the system is out of memory," which is not correct, of course. What you should pay attention to is the available one. But what really matters, I think, when there is a memory pressure, is this column, which is the buffer cache. Of course, you should look at the available, which is the column that give you an impression what really happened in your system, that you have still 11 gig available for your application to use. But also, I think from a performance engineer standpoint, you should know what buffer cache actually is. Let me show you one thing. If we go back to the free command, but this time I want to use man free. Okay, I'm gonna look for buffer. Okay, so the buffer, of course, is just a metadata. You'll see that the buffers goes up whenever you have, for example, direct IO. We'll see what we have in the system, but this is not what I'm looking for. Actually, I want to know what cache actually is. As you can see here from the memory used to be the page cache and slabs, used by the page cache and slabs, cache and slab reclaimable. And this is what I want to explain here. What does that mean? Let's go back here. Okay, so when I go to actually, free dash h is not going to help me here. Let's say free dash k. Okay, when I go to proc meminfo, I'll see something here called cache D, which is this one, and there is something called slab reclaimable. Okay, so of course the buffer, this column equal the buffer plus cache, which means this one, buffer plus cache. Let's see what is the buffer. Usually in this case is going to be zero. It's nothing buffer. Okay, buffer dirty. This one. Sorry for making too much time to get it. Yeah. So yeah, in this system we have buffers is zero. It's not always the case, but in this system, yeah, it is zero k. So the buffer cache, as I said, it is the buffer plus the cache. But the cache itself in free, it is not just the cache D. You have to understand this, that the cache is actually cache D plus, as you saw from the main page, plus the slab reclaimable. Okay, let's start by the easiest one, which is the slab reclaimable. Actually, when you look at the system, slab top dash sc, okay, and you go here, you'll see that the slab is basically the heap of the kernel. As you can see, you'll find something, for example, like d entry. You'll see the entry every time you access a file or a directory. Uh, the kernel is going to take like a hash, put it in a hash table, do some calculation, put it in a hash. So it's not going to work through the file system every time you're going to access that file or that directory. So um, yeah, so there is a hash table called the entry. So it's going to to help the system, so you won't go through the file system every time you access one file. So the next access is going to be way easier because you know exactly where that file exists in the file system. Okay, so this is the entry, and there is also the XFS inode. Also, we have the buffer head. This one is basically for the direct IO. We have the buffer head is just an information about the file, the inode. Okay. Um, we have the inode cache. This one. So those actually the first thing that if there is a memory issue are going to be reclaimed by the kernel. So usually with the default configuration of the kernel, every time there is a memory pressure, the first thing to be reclaimed is this slab reclaimable. This one. Okay. So, as we said, which is, as I said, it is basically the entry, the inode, the buffer head, those kind of stuff. Okay. So, as I was saying, the buffer cache is just the cache, which is this field with slab reclaimable this field. If we do calculation, we'll find them almost the same. Okay, I've been doing some. Okay, go here to the cache, for example, this. Okay, paste plus slab reclaimable. Okay, did I did plus plus Okay, paste equal. So equal 21 something. It's basically or almost the same. Don't forget there is a time difference between what we take when we take this one here and when we take this one here. But yeah, this is what the buffer cache is the buffer plus the cache. The cache is usually the cache D, and the cache D plus the slab reclaimable. And you have to know that in the cache D also there is so many fields that are already included in this one. So if you do calculate this column here, the numbers, you'll find out it is way more than what you have actually in the system, because some fields are including another field, and those what is included in the cache D already mentioned here. For example, let me give you what the cache D you'll see. Yeah, you'll find, for example, cache D included the shemam here, which you see here. This is the shared and the free. Okay, the shemam is basically there is a two-way of there is two-way of using the shemam. There is one by backing up the memory in the MPFS. For example, here you see, since this is a Postgres server, if we go to dev shemam, you see all those files. Okay, let's do this du-sh. Okay, those are all the files existed in the shemam. Okay, let's do it. No, not like this, sorry. That was wrong. Let's do this. Okay, if you do calculate those and IPCS IAM, those for the interconnect communication, we only have 56 byte, and there is number of attached thread or process that are reading from that shared memory are 85. Okay, so let's go back. If I can show you one thing, not this one. Let me share. This is a book I'm writing actually. Uh, okay. So as I was saying, in the free command there is the buffer cache. The buffer cache is actually, this is not for this is for the sar-r, but let's use it for the free memory. Okay. So in the free, let's say in the free column, we have the buffer plus the slab reclaimable, which has the inode cache, the D entry, the XFS inode. Okay, and we have proc meminfo for the cache D in proc meminfo. All of those are actually inside the free column. Okay, but in the same time, the cache D already included the clean. Okay, let's talk about the clean file cache. Let's say there is here, let's say this is a disk, there is file here, etc. Okay, this is a process, and the process want to read the file from here. Every time the process read the file, this file is the first access. There is something called the do page fault. It's going to be triggered by the OS. Do page fault. I'm not going to write it. Then, because this was TLB misses, okay, then this file is going back to the memory. The next time the process is going to access the same file, it's going to take it from the memory. It's not going to go through all of this. because this is may take like 600 millisecond, and this is like only 100 or less. Okay, I'm not sure about the numbers, but I think you get it. Uh, so every time the process read the file from the disk, it's going to put it here in the RAM. So the next time is going to be way less time to access the same file. Linux preserve that file on the RAM, and if that file is the same as it is in the disk, it's never changed, then it's called a clean file. Okay, so what the system actually do when there is a memory pressure, the kernel is check. There is something called LRU. Okay, just an algorithm, or let's say it's an LRU. It's not written for some reason. An LRU. Okay, the LRU actually have four lists. There is the active file, which means that these files are used constantly by the process. So they are active and they need to be in the memory. And there is another type of file which is the inactive, which is another list in the LRU. Okay, we'll continue the rest of the list, but the active is used actively by the process. The inactive, it has been like 30 second or something. There is a timer to uh, that it wasn't used by the process. Okay, so it is inactive. When there is a memory pressure, what's going to happen? The system start to reclaim the memory from the slab first. The inode and the D entry are going, and this is just the default behavior. We'll talk about how to tune it and how this is going to be later. But for now, let's talk about what really happened in the default configuration if you never touch any knobs from the kernel. Okay, so the kernel start to get rid of the inode and the D entry and the XFS inode. Then what's going to happen? Is going to another level, which is the inactive files. This one is going to be the next victim. Then after the inactive, the system is going to check the active, which is why we say this is part of LRU or not, because the LRU, as we said, there is four lists: the active, inactive, and also there is the active anonymous. I'm not going to write it, and inactive anonymous. What anonymous mean? Which is mean is not backed by any file in the disk. If something is really the process is using in the memory, but this like the heap, for example, or the stack. Okay, if this is something in the memory is not backed by any file in the disk, that's called anonymous. Why we are separating them? Why we are not using the same the same name by say active and inactive? Why it is we saying that we have to backed or not backed by a file? Because when you're trying to when there is memory pressure in the system and the kernel start and the key swap D actually key swap D, which is responsible for reclaiming the memory. And there is two knobs to that actually there is two things that related to when kuswapd active or not, which is one there is uh, something we call the water watermark, which is the mem free. I'll show you this knob. Okay, but we are not going to touch it for now. Says control dash a grab. Okay, let's say, because I think something like this. No. Okay, let's say this. Okay. The overcommit, we have Little bit of discussion about this, but not enough. We'll talk about later in another video. We has we have something called VM, huge pages, overcommit. Okay, let's see. Okay, maybe do this. Free. Yeah, this one. You see, this is called the watermark. What does that mean? The system doesn't allow the memory to be less than this value, which is like 67 meg. Okay, what does that mean? When the system goes beyond this value, the key swap D, usually, as I said, there is two parameters that related to key swap D, but this is one of them when it is less than this mark. Also, there is by default something related to the ratio, which is the timing, which is 30 second. When it reaches 30 second, the key swap D wakes up and try to reclaim more memory. Okay, and both parameters are in fact can be tuned. Okay, you can modify it according to your workload. Then, as we were saying, there is the active file, the inactive file, which means it hasn't been used for some times. There is the active anonymous, like the heap and stack, what we were talking about. Uh, that the active, which means it is actively used by the system. Inactive, it hasn't been used for some times. Okay, and this is key swap D. When key swap D wakes up, because it reached the 30 second or the memory is less than the mem free, this value that we were talking about. Okay, key swap D wakes up and try to reclaim. When it starts to reclaim, the first thing to take off and the first victim is the inode cache, the entry cache, which is the slab reclaimable, as you can see from the mem info we talked about. And also there is the cache D, which included so many fields. Like I said, the shemam also is part of the cache D. Yeah, and the key swap D started from the inactive files. After the inactive files, it goes to the active files. Okay, why it choose to use the active and inactive file? Because it's easy to reclaim this from the memory. You can just drop the files and you already have them here. Okay, since they are clean, you didn't change anything from those files. You can just drop them from the memory and you already have them in the disk. So when you need them another time, you just go on to load those files to the memory. Okay, and the anonymous. Okay, let's talk about the anonymous. The anonymous, since they are not backed and actually, the anonymous are not part of the cache D. So just so you know, this is not part of the cache D. But since they are part of the LRU, I want to mention them here. Okay. So the anonymous, since they are not backed in the disk, what's going to happen? The kernel is going to swap them in the disk. This is going to be swap. Okay. This is going to be swapped. And you know, swap is actually expensive, because now you will write into the disk, and another time, since they are not actually in the file system, so when every time you need them, you're going to take them back from the disk. What does that mean? Okay, so uh, that's mean you are actually, your bottleneck is the disk. Okay. um, okay, so as I said, there is the clean file cache, the inactive and active file, and there is of course, the shared text, of course, like the libc, libs, tdc++, etc. of the binary. Those are active and inactive files, and those also included in the cache. We have the dirty. Okay, so what is the dirty? when the kernel change a file, for example, let's say it takes a file from here, put it in the memory. The process start right into the same memory, changing some stuff. Let's say it uses malloc, then uh, Berk here to add more size to the file and start writing in it. What's going to happen? To write this file to the disk again is going to put it in something called dirty. If you go here to, let me go back. Okay. Uh, okay. This value. If, as I said, yes, okay, we have it, but let's take it again. Okay. As I said, to write this again to the disk, it's going to the dirty. Then from the dirty is going to be written to the right back, which means that it is writing it to the disk. Okay. Then it's going to take those value, put them here. Then when they are already written to the disk, this is going to be cleared from the memory. Okay. This one. The right back is going to be cleared from the memory. Yeah, let's go back here. Let's take this again. Okay, so when uh, when there is as we said, when the system is trying to write to the disk, it's taking it from the dirty to the right back, then from the right back. If you are writing to the NFS, you will see it is going to from the right back to NFS stable, which means it's going to the disk, the network, and to make sure it is written to the NFS server, is going to wait until the NFS acknowledge, then is going to be removed from the NFS unstable. So if there is NFS involved, dirty to write back to NFS. As you can see here, you see there is NFS unstable since we are not using NFS, it is not written here. Okay, so um, and also we have shemam. I showed you exactly where the shemam exists. Shemam usually use the two type. There is the TMPFS file system. That's why actually shemam is not. It used to be in the old version of kernel of Linux kernel. It used to be treated as anonymous, since it is not uh, backed up by any file in the file system. But for now, so it is used as a separate type, actually a separate type of files, and it is part actually of the LRU. I removed the LRU. It is part of the LRU, is treated as a file, but actually there is no file in the disk. It's all of it is in memory. Okay. And it is swap only. It is not going to be dropped or so. Yeah, there is a cost in it. Okay, so here I'm just trying to tell you exactly if you want, for example, to clean it by yourself. There is an issue happening. You want to and you want to free some memory from the kernel. You can use echo1. I'll show you this command. Okay, but if you want to clear the slab, you have to say echo 2. For example, the slab here, echo 2. Yeah, let me show you the command. I think I have it here. Not this one. Okay, actually, we have it here. Uh, let's do sys control. Yeah, this command. Echo 3 means that you to drop cache. It means you want to drop the file, the slab reclaimable, and also you want to drop the active file and etc. Those two, as I showed you before. Okay, those two, and the shared text. So yeah, this is the command if you want to look at it, find it in Google or ask ChatGPT about it. Okay, so as I said, they shared the cache, the free here, and let's go back. The free, when you type free dash h or free dash h for human or free dash k for to make it easy so you can understand what you have from cat proc meminfo, you'll find out that buffer cache is actually buffer plus the cache d buffer, which is here 0 plus the cache d, and the cache d you already know that the shemam is part of it, the active file is part of it, the inactive file is part of it. Okay, and also you will know that the shemam is part of it. Okay, the shemam, as you can see, it is almost the same value, but yeah. Uh, you might say why we are talking about all of this and how this is important. You'll understand later when you try to tune your system. You'll understand why you need to know this. And yeah, maybe because this video is becoming too long for me, so and maybe for you, people don't watch 2 hours of video anymore. So let's keep it simple. But if you want to learn Linux and you want to learn when there is a problem, how do you troubleshoot it, how to understand where the memory pressure is. The only thing I want to say here, I'm going to be honest with you, I'm using free just for out of habit. I'm not a big fan of free command, but since I've seen people are using it and taking the values the wrong way, I just want to explain some of the things. But yeah, if I just showed you the command, it's not going to be helpful for you. I know this because I've been through it. So I hope this video will helpful for you. I hope I wasn't explaining things. I don't know. Maybe you get bored from this video. I hope you enjoy it. Uh, and yeah, thank you guys. Let's see each other in another video. I think I'm going to build on this. Maybe start showing you actually what I'm using after free dash h, which is SAR command. SAR is and the SAR dash r is going to be like show you uh, whenever there is a memory issue, and SAR dash b after it's going to show you where the issue is actually. SAR is like a Swiss knife. You can use it. Me personally, I always start with the SAR command before going to the any eBPF tools or BCC tools. This is my go-to. Okay, but to understand it, you have to understand how the system works, how the kernel behaves, what value you should tune, etc. All of the things that we might talk about it in the next videos. Like I said, I hope you enjoyed this video. Thank you guys. Thank you. Bye.